I think now we're moving from the world of dead liquids to world of liquids that are alive.
Yeah, well, liquid is the strong word. But,
It's a strong word.
yeah. Okay. Well, yeah. Thanks for having me. This is first time I give a talk like this. It's a real kick for me. So hopefully you find it enjoyable. Yeah, I'll tell you about a theory called flocking, which is hilariously a pretty famous theory in condensed matter physics, which is not something that I would have expected. And I just want to shout out all my collaborators. So in particular, Eli is just wrapping up his undergrad degree at Brown, and he has many competitive graduate offers. So keep an eye out for him, try to recruit him and all that. He's outstanding. He was with us for one of these research exchange summers. And Marvin, I believe, is starting his postdoc at Chicago this fall. So another person to look out for. Aaron is a postdoc at Boulder, and Andy is my advisor. And our manuscript will appear shortly. There's a few calculations that we're wrapping up, and I'll tease those near the end of the talk if there's time. I should say I feel that the talk is pretty short. I think I have 45 minutes, so feel free to interrupt me with questions, and I'll do my best to answer those. Okay, so let me begin by introducing the subject by showing you a video of some really nice birds. These are birds somewhere in Canada, which is where I grew up. And yeah, so we see some collective motion. And indeed, even in 2D, which 2D birds, well, maybe the surface of the Earth is roughly 2D. Even in 2D, though, models of self-propelled spins that have short-range interactions seem to show some long-range order, collective behavior. But in 2D, for short-range interactions, we have Merman-Wagner theorem that tells us we should not expect long-range order in 2 dimensions. And in fact, provably, this will never happen, right? So what's going on? So let me give you a taste of some of the literature that's tried to get at this question. In particular, I think it started in roughly 95, where Viksak and many other authors whose names are not known came up with an off-lattice microscopic model for spins that move. And then later that same year, Toner and Tu wrote down a phenomenological field theory to describe the same system. And as recently as 2011, I guess Toner was still working on this problem. So he studied something called Malthusian flocks, romantically named Malthusian flocks, which are ones where the birds can die. So in effect, you have a constant density. So you only have to keep track of the velocity field. So this is another effective field theory, but just for the velocity field.
If they can die and have constant density, you must have some births as well.
Yeah, you can have births as well. Yeah, sure.
The fly, they like you go to the fly?
Yeah. That's it. No. Amusingly, the terminology people use, "death on the wing," is what people say in the title of some of these papers. So
no, that's easy to believe. What about birth on the wing?
Yeah, I know, but look, you do your best, right? Anyway, I guess something that I've always found puzzling about this model in particular is that they're claiming long-range order, but they're keeping around some degrees of freedom that have finite lifetime. So really, like if you had some Goldstone mode, you'd think that in a true effective field theory, the only degree of freedom you'd have to keep track of would be some angular variable telling you the direction that the birds are flying, the direction of their collective motion, yet they keep a longitudinal velocity as well. No big deal, but that's going to motivate sort of what I'm going to talk about when I talk about our work. Okay, good. And then most recently, there's this really nice PRL from that was published in 2022 that shows that some non-perturbative effects that are very subtle can actually destroy the long-range order that Toner claimed in 2011 for this model of birds giving birth and dying on the wing. So that was sort of what got us interested in this model, or in this problem, I should say. Maybe there are non-perturbative effects that you have to be really careful of. Just really complicates the story. And that's all I'm going to try to do in this talk. I'm not claiming to have a theory of flocking or anything like that, obviously. But I do think that we can complicate the story in some non-trivial ways, and I'm interested to hear what people think. Yeah, please.
So it seems like in this slide, you're focusing on 2D, and there's a puzzle. There's a question mark.
Yeah.
Now in 2D, and for finite size flocks, I would then wonder, can one really distinguish, or does one even care to distinguish long range order, quasi long range order? Are these
Well,
U1 spins, or is there? Do we even we only expect quasi long? I guess what I'm trying to say, there are finer questions which seems like, given the size of the flock, I'm like, who cares, right?
Yeah.
There may be more interesting questions.
I'm with you. I think whether one cares may be a matter of taste, but yeah, to get to my punchline, yeah, maybe I'll just do that, and then
That's
if
fine.
you have more
You wanna
questions,
answer
we'll
later.
yeah, let's do that. So, okay, and this is another great reference for this problem. Yeah,
Is that where you're from?
yeah, I grew up in Halifax. Yeah, that's right, and I never talk about it though. So.
Are you bird watcher?
I was a bird watcher as a kid. Yeah, I love my iPad background is some nuthatches in Nova Scotia. So great. Okay, so let's get on with the temptation to be too cute when discussing this topic is overwhelming almost for me. So okay, so let me now give you the punchline of the talk, and then I'll dive into the motivation for the rest of the talk. So what I'm going to present is a model with classical two-component spins on a 2D square lattice. And I'll keep track of only the orientational sort of order parameter or degree of freedom. And the log wavelength description, which is technically non-hydrodynamic by my definition because nothing's conserved in this model, but the long wavelength description is going to be identical, almost identical to the model that Toner has studied in 2011. And in particular, it has this form. So the terms that are supposed to be in blue, I hope it's showing up, are kind of convective looking term that tells you that birds want to fly in the direction they're pointing, that spins want to propagate in the direction that they're pointing. And then on the right-hand side, we have the yellow terms are is just a normal diffusive piece with a Gaussian white noise. Yeah? And what's doing a lot of heavy lifting is the order gradient cubed terms that I put in white on the left-hand side. And my claim is that at long times, you can write down a probability distribution for all of the theta degrees of freedom, which living on a lattice or in continuum, whatever. And we've shown that it's exactly the stationary distribution Hamiltonian for a thermal XY model, XY magnet. Yeah. In particular, what that means is that there's no true long range order, quasi long range order, fine. But provably, since it's a 2D XY model, this theory has no long range order. So we found a theory of flocking, at least one lattice model for flocking that seems to not have long range order, and we can prove that. So in the rest of this talk, I'll give you some details of this, and the reason I want to go through the details and motivation is, it's a workshop. I think that this will prove to be an instructive example of the line of thought that my advisor Andy has introduced to us yesterday. So I'll review that along the way, and then I'll try to argue to you that even though we have a stationary distribution that's featureless, essentially in this way, almost featureless XY model, that we still have a non-trivial dynamical universality class. And this is not so unexpected if you know anything about the KPZ 1D equation. Yeah. Okay, any questions before I dive into the physics here? Yeah, please go ahead.
Feel free to defer if you're about to say these things.
Yeah.
But order Napa cube, is that a third derivative or a derivative cube?
Third derivative.
Okay, so this is linear and, oh no, it's not linear, right? Okay.
This is still not linear because of the blue things.
Yeah, and so this is.
And we could have more nonlinearities too, that lots of more irrelevant things, yeah.
Toner to unit velocity.
This is Toner 2 with a unit velocity, yeah.
Plus y.
Yep, that's what I'm saying. This identical to Toner 2 if the longitudinal velocity has already relaxed, blah, blah, blah. Yeah. Good enough? Great, okay. More questions before I... Okay, so with that, I'll move in. So let me just remind you about this idea of time reversal symmetry that we were introduced to yesterday. So let's start with some classical degrees of freedom, which for me are going to be these spins that are going to interact with the thermal bath. If you look at a true microscopic description of a model like this, you'll find that you have time reversal symmetry because you have a bunch of Newtonian particles bouncing around and hitting each other, right? F equals ma, time reversal symmetric. But when you coarse grain by integrating out the bath, you get a stochastic equation that looks something like this. So rate of change of one of your fields is equal to what I'll call a force. It's a force in the sense that I guess Aristotle understood it. And we'll have a Gaussian white noise in this case as well. And I just need to specify the variance of the noise. So I'll call it a constant Q that will just become a delta function shortly. But the point is that this equation doesn't look like it has time reversal symmetry, as we were told yesterday. But we can make it have time reversal symmetry, or at least understand the consequences of microscopic time reversal symmetry on this coarse-grained macroscopic field theory. And the way to do that is, first we want to think about the Fokker-Planck equation, which is completely equivalent, and which I'm parametrizing in terms of a differential operator W. And this Fokker-Planck equation may have a stationary distribution. So in the limit of t goes to infinity, set the left-hand side to 0 and maybe try to solve. But for us, we'll start with this stationary distribution and look at things that are consistent with that. I'm free to call it e to the minus phi if I want, in analogy with thermodynamics. And of course, for this model, I'm going to postulate. So we're going to start by saying that we want that stationary distribution to be a thermal XY model, as I previously motivated. And then the result that I'll just claim and not prove, but it was discussed a little bit more in a little bit more detail by Andy yesterday, is that this dissipating theory is compatible with microscopic time reversal symmetry, which also goes by the name detailed balance, if the following transformation holds on W. So you take W, you take its transpose, like in quantum mechanics, in the sense of a differential operator, and then you multiply and divide, you make a similarity transformation with the stationary distribution itself. This is what time reversal symmetry means for a dissipative theory. In this sense, the diffusion equation is time reversal symmetric.
Means that your steady state is kind of equilibrium.
Yeah.
It's kind of zero flux in the probability space everywhere.
In the limit of infinite time, you have zero flux in probability space everywhere. Yep.
Because then the equation will have different solution too.
Yeah,
Fluxes, yeah?
Sure. That could be so. Yeah. So we're going to look at, it's an assumption for us that we reach a long time stationary distribution. Now you could ask, okay, could stationary distribution be non-local, blah, 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 have high body interactions? Sure, but for us, we'll take this nice local guess and derive consequences. Yeah. Okay, and then so this transformation of W implies the following relation for this force F. So the first piece, which is the only one that happens if Q, the noise, is constant, this is nothing but time-dependent Ginzburg-Landau theory, right? So this is like gradient of free energy is proportional to this Aristotelian force. And this Q, since it's a noise variance, needs to be symmetric. Yeah. So from a model building perspective, what's the most general symmetric matrix you can write down, or maybe the simplest, depending on whatever you want to do. Okay, so in this model, I'm going to take Q to just be a delta function. So we'll have uncorrelated noise. This is physically relevant for something like a thermal bath. And just for the rest of the talk, I'll also define mu. It's kind of like a chemical potential as the gradient of this free energy that I've defined, where the free energy is this phi thing, which is the stationary distribution. In this case, from the previous slide, Langevin equation looks like this, which in the continuum limit up to higher order corrections with more gradients is just a diffusion equation. Yeah, so that's the time reversal symmetric part of our dynamics, the dissipative part of the dynamics for this model. This is just time dependent Ginzburg-Landau theory. I'm really not saying anything new here, but I don't need to tell you that. But next, I want to talk about what happens when we break time reversal symmetry, because for a model like something like flocking, we actually don't have time reversal symmetry. Birds don't have time reversal symmetry. Basically, the bird's flying this way and you reverse the arrow of time. Now they're flying this way. You need to also rotate the birds, right? And that's how you get time reversal symmetry. So I drew some cute pictures. So you start with the bird, a bit of grouse. I didn't want to be too ambitious with this model. And grouse is a silly bird. So you start with a bird going up in this direction. If you flip the arrow of time, now it looks like the bird's going this direction, but it's still pointing the first direction, yeah? So then you need to both rotate the bird and rotate your spatial axes kind of in a diagonal kind of way. And I've called that, just to confuse you, I've called that P. I guess I'm used to saying PT, but it's not, I don't think it's quite parity. And then you actually do have a true symmetry. So this at the microscopic level for an active thing like birds, this is the symmetry that we need to enforce, not just T, but only PT. And that's what's going to allow us to write down more terms. So what if we want to include terms that are odd under time reversal? If we write down something odd under time reversal and odd under this P, then we have a nice symmetric term. Well, it's almost exactly the same as what we did before. So take transpose of W, multiply and divide by stationary distribution in the similarity transform. now we just allow ourselves to put a minus sign on the left-hand side. So now we say that the Fokker-Planck generator, W, it's allowed to switch sign under this sort of detailed balance transformation that we're calling time reversal symmetry. Let me just finish the slide and then happy to. So at this point, we get kind of an analogous constraint on what F has to look like if W is going to be time reversal odd. So the second term that you can see, if this anti-symmetric matrix V were constant, this would be a lot like time-dependent Ginzburg-Landau theory. You have an anti-symmetric matrix, though, now instead of a symmetric matrix, which was the noise variant. But the term that's going to do a lot of heavy lifting for us is actually this case where V, it's a nonlinear theory. V has dependence on the field. And so this dB, which is derivative with respect to theta B, if I didn't introduce that notation, this is going to do a lot of heavy lifting in giving us our theory of flocking. But now let me answer Ben's question. Yeah.
So in the active matter literature, people talk about non-reciprocity, and this actually has to do with breaking of PTs.
Yes, that's right. Yeah. So yeah, because I think I have time, I can digress a little bit on this issue of non-reciprocity, and we can talk more after, or you can, even worse, you can read our paper. But we've applied this same idea to understand a lot of non-reciprocal phases of matter, most notably these odd solids and odd fluids that are popular in Chicago right now, the group of Vincenzo Vitelli, William Irvine, etc. These pop out naturally from this formalism. The idea, just for people who don't know about non-reciprocity, is if you have a gas or maybe a fluid, maybe foxes and rabbits or something along these lines, they don't interact reciprocally, right? Because the rabbits chase the foxes, but the foxes, sorry, it's the other way. The foxes chase the rabbits, but the rabbits run away from the foxes. In that case, you do not have time reversal symmetry, even at the microscopic level. Play arrow of time backward, it looks like rabbits are chasing foxes, which doesn't make sense. Yeah. The only symmetry you have is if you reverse arrow of time and also change every fox into a rabbit and every rabbit into a fox. But if you enforce that symmetry, then we're able to understand, if you enforce that symmetry in this sense at the dissipative level, then we're able to understand a whole zoo, pardon the pun, of non-reciprocal theories. So let's talk more after, but I'll move on with the birds for now. More questions while I've interrupted myself? Or?
Actually,
Yeah, please.
so accommodating.
Yeah.
When you say understand, since I'm not knee deep in these exotic or whatever fluids, to me, understand usually means that you have a Gaussian theory that's relatively kind of like there are no anomalies that I don't understand.
Yeah.
But then I can do something with it's epsilon expansion, something like this.
Yeah,
to understand interacting behaviors.
Sure.
I have not noticed that next step in like other non-trivial collective phenomena. By collective, I really mean non-Gaussian.
Yeah, I know what you mean. I think I'll do my best to convince you that there are such effects at the end of the talk. But if you're still not convinced, then we can talk more. But yeah,
So
Tom.
I get a field as well.
Yeah, that's right. That's right. So, for instance,
Find a field that is one or the other.
yeah, that's right. And of course, we heard in the talk by Seth yesterday how a magnetic field is one way to get this Hall component of viscosity. But there are other ways. For instance, if your particles are something dumb, like they're made out of spinning robots, you can also get this same viscosity. But we have this theory that's kind of, maybe what I mean by understand is we have a theory that's almost agnostic to the microscopic details as much as possible. Okay, let me move on. Oh.
VAB is the same as VAB in the first term and the second one. Can you generalize when there are two different antisymmetric? Yeah,
Here?
it must be the same.
Must be the same.
I see.
Must be the same in order to guarantee this property.
So cancel, yeah.
Yeah. So, and let me just emphasize before moving on to the next slide that what we're really doing here is adding what I would call active or odd terms, time reversal breaking terms that still maintain the same stationary distribution. So they do not ruin the long time equilibrium-ish behavior of this model. We can have active matter that still has an equilibrium distribution. Is it all of active matter? We're not sure, but Probably not. Or at least probably some active matter requires a horribly non-local stationary distribution. But we can talk more about this point. I'm not fully sure of the answer. We're very new to the field of active matter, but okay. I'll move on now and actually write down the lattice model that I promised you for flocking birds. So the point is just to pick a VAB that makes the Fokker-Planck generator Hamiltonian kind of for this, some Hamiltonian for the system, invariant under the combination PT that I previously introduced. And here's the answer. So I'm switching this A, B notation for R prime because these spins sit at various lattice sites. I need to write this down. And effectively what's happening is that rotate.
Pointer here.
Oh,
With your finger.
it's more natural.
Oh,
Is
okay,
that I think it's clear what I'm.
That's-
So when you switch the let's see, when you make a shift on the theta field, kind of at every point in space, it's kind of undone by the shift of the delta functions that comes from rotating your spatial axes. So that this is a nice like covariant thing, and it leads to a W that flips sign. Then the point is to compute this term dVVAB minus VAB UB that I wrote on the previous term. That gives you the term that appears in your Langevin equation. And you find the following equation of motion for theta, very complicated, but we can take a naive continuum limit and we find simply this convective piece up to orders and gradient. What's remarkable though is that this equation of motion, if you are careful about continuum limit, there are no corrections that are quadratic in gradients, only corrections that are cubic in gradients. So you expect that these are irrelevant compared to whatever maybe Gaussian fixed point that you're at. And I'll get to that more, but the corrections to this equation are smaller than diffusion.
Because it's four, it could not have quadratic.
Exactly right. So maybe it's not so remarkable, but it's important. Maybe important is better word. Yeah. Okay, any more questions about this slide? It's really a technical slide. Good. So now we put both parts together, and as promised, we get this theory that I advertised at the beginning of the talk. And the rest of the talk, I'll just be exploring some consequences of this theory and trying to make sense, and then maybe I'll be a little bit ambitious at some point if I'm provoked. But and I'll just say one more thing, and then I'll answer Carolyn's question. But I just want to just show you one simulation that we've done, and I'll show you more later, just to convince you that there is some kind of flocking behavior. I mean, it makes sense. It's a convective term, yeah. So no one's going to be surprised. But okay, on the left, so we have time going down on the slide. On the left, we have XY model, totally thermal model, equilibrium model. We initialize some perturbation to spins, and nothing happens. On the right, the spins move roughly in the direction. They try their best to move in the direction that they're pointing, but really they move at the average spin of the average direction of the whole theory. So sorry, Carolyn, I interrupted you, but no, I'm not claiming that. No, it's the simplest one I could come up with, but we don't expect it's the only one. No, and in fact, we have many different discretizations. If you like, you can just think that the same continuum theory can always have many different discretizations.
Right, so then would the like continuum limit be the same?
Yes. Yeah. We believe so. Yeah. Yeah, you put in the noise, well, roughly by hand. But I mean, if you're at a finite temperature, if you're studying a model at finite temperature, you always need such a noise in order to make time reversal symmetry manifest at the level of the coarse grain equations. Yeah.
I mean, if I start finite temperature, but I'm not in contact back, do I really have those?
Then you're not at finite temperature, I think.
Have effective noise on the coarse grain.
Yeah. Well, sure. That's one way to think of it. You could think, I mean, maybe I'm not saying anything mathematically sophisticated, but coarse graining, the noise kind of parameterizes the information you've lost, the errors you could have made when. I hope that helps. Let's talk more later. Let me move on because I'm a little, this is taking, it's not going to be as short as I anticipated. So let's move on. Okay, so the first thing that we did was make one check. I'm claiming that the stationary distribution is the same as XY model. What that means is that all equal time correlation functions, 2-point functions, should agree. And that's exactly what we find. So okay, I've confusingly called the two traces equilibrium and active. Equilibrium means XY model, thermal XY model. People in literature, for some reason, call this an equilibrium model, even though you can be out of equilibrium in that. But okay, I get it. But so okay, the traces collapse. Maybe the colors are hard to see, but it doesn't matter. The traces collapse. So yes, our model has the same equal time correlation functions. Yeah.
Could do it.
Yeah, sure. Whoa. Can we split the difference? Yeah. Oh, perfect. Okay, great. Yeah. Great. Okay, so now you can see the lines. I think the colors are still difficult because I like the black background, but okay. Good. But what's more interesting is if you move beyond equal time correlation functions. So my claim is I'm going to try to show you some data to convince you that despite this unchanging stationary distribution, adding these blue terms that violate time reversal symmetry gives you new dynamical scaling, new dynamical universality classes. As I advertised at the beginning of the talk, this is not unexpected. For KPZ equation, KPZ fixed point in one dimension, steady state is Gaussian and featureless. Yeah. Yet you still find a non-trivial dynamical universality class. So this is not something to be surprised by, but I'll show you some data to convince you that this model is an example of that. I think probably the word you should take issue with might be universality. I may have found a class, but how universal is it? That's something that we're working on. So you need to study a time-dependent correlation function to distinguish from the XY model. And the one that you want to look at, okay, I'll write it with this equation, but I'll show you what it is in a picture. What you do is you take some initial spin, and then you follow it in the direction that it points, because that's the direction you expect it to move, right? If it's a flocking bird. And then at a later time, and at some distance, you measure its two-point function with that spin. So this is a time-dependent and space-dependent correlation function. But for some technical reasons, we like to project out some other things as well. So don't worry too much about this, but all we're doing is projecting out some rotational invariant components to make sure that we get something that's going to vanish exactly for the thermal XY model. So this is the best way that we're going to be able to distinguish our active model from the equilibrium XY model. Okay, the next few slides, I'll show you some numerics simulating the exact lattice equations of motion. So with all derivative corrections technically incorporated for this, but before another question from Ben. No, it's fine. Yeah.
So if you haven't had any questions, you can revise it. Layer to
Yeah.
Some modes and their velocity is not that fine. So
Yeah.
If you look what you're doing here and you look at correlations along the velocity of some.
Linear? No. We're going to measure this without any linearization necessary.
I mean, to do the theory of correlations.
To do the theory of correlations, yeah, one could do this. I mean, I think even in that regime, this thing would be a difficult thing to calculate by hand. I mean, I tried to do it with using this Martin-Suggia-Rose path integral, but I sort of gave up, and we're happy enough with the numerics, but let's chat at some point. Yeah, I hope that helps. Okay, so let me now plot this F correlator. Okay, so here's the first plot. Hopefully the traces are visible. So on the y-axis, I'm showing you this correlation function that I defined on the previous slide and I'm at fixed times as a function of like the distance between the two spins. And the different traces are showing you various times. So, okay, why does the peak move as you increase time? Because the birds fly, right? So that's what we're seeing in this nice plot. And then what do you think is gonna happen? Little data collapse. So we're pretty convinced. I mean, we're doing some more work, but we're pretty convinced that we see this nice data collapse if you scale both time and space together. This is the normal kind of.
So
this is just this is the normal dynamical critical exponent. I think on the bottom, and it's roughly 0.4, but we're still nailing down what that is. Sorry, but
show the definition of that.
yeah. Let's go back. No, that's fine. Yeah. Yeah. Just leave it for a second. People want to take a picture. And in the meantime, I'll ask a question, answer a question. I guess to some degree, you never know for sure in this kind of numerics because we're simulating the stochastic equations. We're not doing Monte Carlo. So in some sense, you never know. But I think the fact that if I go back and show you the equal time correlation functions, these are exactly what you can show that they have to be for an XY model in thermal equilibrium. So we're pretty sure that we've at least the probability distribution has relaxed to the stationary distribution that we expect. Yeah.
In your data collapse, were you going to show a contrasting data collapse for the equilibrium? You know what that is? Because it's a quasi long range ordered state, so it'll have some power laws necessarily.
Yeah, I'm not going to show that, but that's right. There's a T to the something. Yeah.
Depending on the noise and everything.
Yeah.
But is there?
And ours will be slightly different because we have Gaussian noise, not derivative correlated noise. Yeah.
Right. So how different is this from the whatever reasonable equilibrium?
This is different. XY model just should go down, but we could look at some.
I see. Oh, right. Yeah.
Yeah.
So,
Well, actually, this F sorry, I might have even misspoke. This F thing is exactly 0 for the XY model.
That's what I was looking.
Yeah, sorry. Yeah, this F thing is exactly 0 for the XY model.
Because you subtract.
Because we've taken T minus T, and XY model is time reversal symmetric in the sense that I've described. Good enough?
Yeah.
Okay, great. Okay, and then I'll just finish my punchline. We have therefore a scaling hypothesis, and so I said we believe that we have this critical exponent or whatever. Okay, sorry, Carolyn, you can go ahead. Yeah, that's Z, I think. Yeah. Z. Oh, let's sorry. What's your question? Beyond relativistic. No, I think this is a non-relativistic theory. That is funny. Yeah, but no, oh well.
Oh, we don't know what a field theory is.
No, possibly, yeah.
Is there another question?
Yeah, Grisha, please.
Remind the definition of it.
Yeah, no, that's.
Oh, yeah. This thing again, this
You
thing.
might want to put a definition. of that.
Yeah, okay. I'll take.
Yeah, thanks.
Yeah, you're welcome. Okay, let's go. Now we're here. And now we're here.
Okay.
Keep going.
Okay, good. Yeah, right. Okay, good. So I've pretty much finished what I want to get through. So, but I see that I have maybe order 10 minutes left, so I can make a few points. So think of these as appendices if you want, because it's very preliminary. But something that we wanted to do for this model to compare to the nice PRL that I introduced at the beginning of the talk was to study the motion of vortices. So in an XY model, okay, now time is going to the right on this slide, and I'm just showing you 3 snapshots where we start in a totally random state and then relax to some kind of quasi long range order phase. So this is below, I think, the KT transition. And of course, in the XY model, if you wait long enough, you never have any vortices. They interact with the log potential and they annihilate. And in our model, of course, the exact same thing happens because our stationary distribution is exactly the same. Our long time equilibrium distribution function, exactly the same for our model as for XY. So in the rightmost panel for our active model, you also get no vortices. Maybe the only thing to notice is that, I've put some circles where the vortices are at intermediate times, and we have less in our model. It seems like vortices are annihilating faster. So that's something that we're working on quantifying. Have we modified the interaction potential somehow? So some more numerics are ongoing on this point, but I think it's likely that we have maybe to be romantic, anomalously fast vortex dynamics or some title like this.
Can you start from the right and put 2 vortices? Because I mean, there are the Coulomb forces, and there's like all of this sort of diffusion.
That's what we're doing. So the numerics that are running on some computer in Colorado right now are vortex, anti-vortex, and then you just watch how long they take. Yeah, that's all we're doing. Yeah. but I don't have plots yet. Sorry about that. Yeah, please, Alan.
There are usually scaling dynamics for the vortices as well.
Mhm.
And a la Hilbert and so on.
Sure.
I'm wondering if you see that for the active, if you see scaling dynamics in your simulation for the XY, but also for the active model, now they.
For the XY model, yeah, we've done all of our due diligence on our simulations. We're confident that they're correct. I haven't seen that scaling precisely. Yep. So maybe I haven't done all my due diligence. But for the active model, we expect a different modification to the exponents or whatever. If that helps, but I don't know if I can say more than that. Was there another question? Okay. So now let me talk again about this PRL that I think quite highly of. So for them, the mechanism of ruining Toner's argument was non-perturbative effects from like these wacky vortices called asters that are actually going to show up and proliferate. And they nucleate and ruin long-range order. For us, we're not seeing them, of course, because we've guaranteed that our stationary distribution is featureless. But what we can do is turn off one of the pieces kind of along the lines of what Grisha was suggesting earlier. So we just do this by hand just to sort of see what happens, check for our model. If we do that, then we'd see actually the exact same qualitative physics. We're doing a much smaller scale simulation here. We'll have better ones when we publish, but we're seeing the exact same physics here. So somehow, and the interesting thing is these VAB mu terms in continuum have 3 gradients. So somehow adding this term that people would usually forget about really qualitatively modifies the long-time physics of this model. Maybe it's some kind of anomaly. I don't really know if I have a good answer to what that is, but it may be similar, you know, flows with almost no viscosity are very different from flows with 0 viscosity, right? There are anomalies like this that show up in hydrodynamics. Okay, so now, okay, I still have 4 more minutes left, so I'll give you some, the red means it's even more, this is appendix 2, if you like. But I want to move now and actually try to look at, do a very simple naive renormalization group analysis of this kind of model and compare it to the one that Toner has presented. And in order to do that, it's better to move to the Lagrangian picture rather than talking explicitly about the Fokker-Planck operator like I was doing earlier. This was introduced in many of the talks yesterday, so I won't spend too much time, but one can make a path integral, change Fokker-Planck equation to path integral with the help of an auxiliary field pi. So kind of like in quantum mechanics, the derivatives in the Fokker-Planck equation turn into this pi momentum conjugate field. And your Lagrangian will take this form. And time reversal symmetry, as was explained by Andy yesterday, has a really nice form in this field theory. It's just a shift symmetry on pi, which is easy to implement in a field theory. So this is one reason to work with these kind of theories. So looking at Toner's 2011 paper, he had an equation like this. So here, you don't need to look at the details too much, but V is a full 2-component velocity field. So it has both the orientational degree of freedom and also a longitudinal one. What's going to happen is that depending on the values of A and B in this equation, the longitudinal one, like at long times, is going to kind of go away, and you'll be left with, and that's how this model turns into roughly hours. And if you linearize around an ordered phase and set the scaling of the x derivative just to be what it has to be, he has argued that you get these scaling exponents. Sorry, that's not the right word. These scaling dimensions, scaling dimensions for maybe engineering dimension for the various operators that you care about. So I'll just leave these up, but yeah, and you can read the paper for details. It's a dynamical RG calculation. For us, this is what our Martin-Sigia-Rose Lagrangian would look like. So here, just to make things a little neater, instead of writing everything in terms of the cos theta, I've introduced this n unit vector, cos theta, sine theta. So this is what our Martin-Sigia-Rose Lagrangian looks like. We can do, from simple calculations, the same kind of analysis, linearize about theta equals 0, and assuming that we're near the xy fixed point, and we find the following scaling dimensions, engineering dimension, whatever. I'm no field theorist, but you get the point. the puzzle from this slide, at least in my view, is that the third derivative corrections that are also ignored by Toner are just as irrelevant, if not more, for us as they are for him. So we really don't expect that they should affect the long distance behavior of the system, but they do. So this is some kind of puzzle. Maybe there's a resolution, because I'm no expert. I'm just going to finish up in one sec. So then I'm no expert, but there seems to be something funny. Maybe the naive RG perspective that I've introduced is just not good enough. One has to be more careful, calculate the flow, etc. I'm not sure. I think that's all I wanted to say. So thanks a lot for listening. Yeah, Karen, go ahead. Yeah, okay, let's go right back. Well, this is because yeah, good question, but you're linearizing a state around a state where everything's pointing in the x direction. So the y is kind of like it would be like a Goldstone mode if you really had FSB.
But yours is
Yes. So that must be because we don't have this or something. Like, because the only field that we have is theta. Yeah. So theta can good.
Yeah, maybe this is a related question, but I'm perhaps a bit confused because you were emphasizing throughout the whole talk that your theory is essentially Toner 2, and then now in this field theory, the engineering, the scaling dimensions are so different.
Yeah.
Even at the Lagrangian level. So what's going on here? Is this just the choice that you made about the fixed point you're expanding around, or is there something more subtle about MSR?
That's a good question.
Can I actually add?
Yeah, please go ahead. Yeah.
Because I think these are all related.
Yeah.
You know, once you do dimension counting and field theories, there's a grinder that we'll go through, right?
Yeah.
So I think one of the questions, I think a related question is that you already mentioned that this is expanding about the oriented phase.
That's true. Which does
So that suggests, so the question I had, which I think resonates with that, is that usually when we write down fixed points that are interesting and gapless, we want to make a list of relevant, marginal, and irrelevant operators.
That's true. Yes.
So for the equilibrium XY model, the symmetry breaking field is a relevant operator, and its dimension is changing as a function of where you are in XY phase.
Fair enough. Yeah.
And it remains relevant at the critical point.
That's true.
Right.
Yeah.
So I guess the question is that this suggests, the difference in Y suggests that the relevance of the relevant operator is very different about these two theories. Basically, if there's a predator from this side, is the bug going to get oriented?
Right.
Run away, just like a magnet would polarize with a.
Yeah. Look, okay, maybe I can.
I'm not sure if these questions are related, but it seems like they are.
I believe they are. So let me say what I can. I mean, I'm no expert, so if anyone wants to talk at the board, and maybe this is probably all we're going to say in our manuscript about this puzzle, and I wouldn't take the dimension counting too seriously by any means. I think if you can take anything from it, it's just to say that it's not crazy that you expect a non-trivial dynamical critical exponent because you have wacky scaling, even at this naive level. But maybe that's the extent to which I want to buy anything on this slide.
Do you see any non-reciprocity?
No, non-reciprocity would be something that we'd have to put in by hand. So that would be interesting. There you would have like blue spins and red spins, and the blue ones want to attack the red, and so we could do that too. But I mean, Vincenzo Vitelli's group has studied non-reciprocal flocking in an excellent fashion. So,
all right, I think we're actually
over time. Oh, great. Okay.
All right, let's thank you.
Thanks.
That was great. Who's next? I don't have a schedule handy.